So, okay, as I was saying, we'll see what an adversarial perturbation is. And in particular, we will see that in the context of convolutional neural networks. So, as most of you probably know, a convolutional neural network is a particular architecture that goes under the big umbrella of deep learning. And it's a kind of artificial neural networks able to autonomously learn a good set of features in the case of images, in image scenarios. And this architecture is not actually very recent because it was theorized for the first time in the 80s of the past century, but it started to get attention in 2012 when its first real implementation was done and won the 2012 ImageNet Challenge. And the reason why CNN are very interesting is because, as I said, they are able to learn, autonomously learn a set of features in the case of image processing. Actually, in the past few years, they were extended to be able to work in several different scenarios, including audio, text, and so on. But they were intended and they burn for the case of image processing. They do that by using convolutional layers. So actually, it's quite simple, the idea underlying, because the idea is simply to use artificial neurons to implement the convolutional operation and make the convolutional weights be learned during the training procedure. The nice thing is that it has been proved that the way they learn, especially when the training is performed on a very big data set, such as the ImageNet one, they tend to learn hierarchical features in a way that it's somehow close to the way human brains learn. So the layers closer to the input start to learn simple features like how to recognize simple shape like lines, angles, and so on. And as we go towards the end, so towards the output layer, the features learned are able to recognize more complex details like an eye in the case of face or the whole face at the end of the architecture. And this is very interesting because despite what happens in other scenarios where the domain expert has to design a new set of features moving from one domain to another before extracting them and feed them to neural networks. In the case of CNN trained on big data set, the learned features are usually very, very general. And so it's possible to apply and to use transfer learning and other knowledge transfer techniques to reuse the learned knowledge in a possibly very different scenario. And this has been massively done. So we can see that nowadays there are tons of papers focusing on the use of CNN in very different scenarios. And I'm talking about CNN pre-trained, for example, on ImageNet. And so for the most important example are the use of CNN pre-trained on ImageNet and then used for biomedical image processing. So image is very, very different. Or, for example, used on spectrogram of audio samples. And they still works. The problem is that when you do that, there might be some consequences that it's important to keep in mind. And in particular, this spread, the spread of the use of CNN, and in particular of deep learning, all over in a very different set of application may be wrong. And we have to pay attention to what can happen. So the first, let's say, world scale, large scale problem example arose in 2012 when Staples decided to use artificial intelligence in order to change the price or to provide a discount and offers to some customers. The idea was simple and was actually quite fine because they simply wanted to, propose to offer deals to customers closer to a competitor store. The problem is that it turned out that people that are far from competitor store were those actually with a low income because they were living far from the center, for example. And so people with low income got higher prices and so on. And this is clearly unfair. Another a little bit more crucial example comes with Google. Google, as you know, is one of the pioneers in the use of artificial intelligence with mass, so with the large public. And they were the first using AI for automatic tagging of images. The problem was that with their first version, Black people started to be tagged with offensive and racist tag. And also this happened later in time with Google offering lower paying jobs to women and to Black people again. And as you can see, this is definitely unfair. This is another example, and in my opinion, this is the worst example, and it's based on the Compass assessment algorithm. This is an algorithm still used in the USA, at least in some countries of the USA, and it is being used by the Justice Court to decide, or at least to help during the process of deciding the amount of years for a person. And this is bad because it has been proved that, it has been shown that this algorithm has both gender and ethnicity bias. So for example, women or young person or Black people usually got a higher risk even if they actually committed a very small offense. So clearly, in all the examples I showed you so far, the problem is never AI, because AI is just a tool. And as a tool, the problem is always in the way we as humans use it. And in most of the cases, in most of the example, and for example, in the case of Compass and of Google, probably the problem is just in the data they used to train the algorithm. So the bias was within the data, clearly, and not in the algorithm. But despite this, the problem is still there. So how can we, let's say, defend against this? Is there any way to somehow force a more ethical and fair use of artificial intelligence? This is what I'm working on right now. And in this presentation, we will only focus in the case of image processing, but most of the ideas and scenarios I'm going to show you can be extended, can be applied also to different scenarios like audio or text processing. So before we start, I don't know why this slide is not showing correctly. Anyway.
I'm sorry, Stefano. I'm really sorry I have to interrupt you once again.
No problem.
So since now you're the host, if you see anyone is waiting in the meeting room, could you please let them in if you can see them from the thank you.
Yeah, there are 3 people in the waiting room. Okay, but can I give you the host back somehow? And
yeah, you can do that in the you look at the participants at the end.
No, I know how to do that. I'm just worried about what happens. Probably. Okay, let's start.
I think I can continue for the recording, so it should be fine. Yeah, I'm the host now. Yeah, sorry for that.
No, it's fine, and I can still share my screen. Okay, great. Okay, great, perfect. Okay, what I wanted to show you here is that. Okay, so we said that somehow CNN are, let's say, inspired by the human brain, and they tend to behave like human vision system. So we know that we can mislead the human visual system. So I'm showing you right now an optical illusion, And for most of you, it's very hard to say how many circles are in the picture. Previously, there was an overlay to help you see that actually there are just two circles. But the point is that if it's possible to mislead the human eyes, and since it seems that CNN behave, or to some extent, like the human eyes, can we also mislead a CNN to force, for example, it to behave in a way that it's a little bit fair? Well, let's try to do it together. Can someone tell me what animal is in the picture?
I think it's more like a cat.
Okay, yeah. Actually, it looks like a cat. And also, if we try to classify this picture by using a CNN pre-trained on ImageNet, for example, well, this is recognized as a cat with a very high probability. But what happens if we add some noise to this cat image? Clearly, I'm not talking about a general noise, but about a noise crafted with the aim of misleading the target CNN. As you can see, we obtained the image on the right. And for a human person, this is still a cat. I hope for most of you, this is still a cat. But probably you can see that the image is a little bit more noisy with a little bit of blur in the background, some strange colors close to the eyes, and so on. Well, what happens is that if, despite the fact that this still looks like a cat for a human operator, this suddenly becomes a dog for the same CNN I was talking about before. And also in this case, the network is quite sure that's a dog, that picture belongs to a dog. What I showed you before, what I showed you just now, is called adversarial perturbation. And the term refers to a set of algorithms intent to craft this noise. So there are several ways to craft this noise, and they are intended to mislead a target CNN. The math behind this is quite simple because, as you know, what actually any kind of machine learning algorithm does is to create a separation hyperplane in the feature space. So what an adversarial algorithm does is to simply change the pixel values in order to move a target sample from one side to the other side of the decision boundaries. Clearly, closer the target sample is to the decision boundary, easier is to perform the attack. The problem is that we can show that it's possible to use these techniques against or in favor of a subject if CNN are used in this context. So I'm going to show you a couple of examples. The first one, when we want to use adversarial perturbation to protect the subject privacy. And in the other case, we want to use the same attack, but against a CNN when deep learning is used to enforce security. So probably most of you know what a biometric is, but you might not know what a soft biometric is. Soft biometrics are the set of biometrics that still are able to say something about you, like gender, ethnicity, age, skin color, and so on, but not enough to uniquely identify you. Despite you can say, or you may think that it's fine to collect soft biometrics about people because they are not enough to uniquely identify a subject, actually it's not good at all because they can tell you a lot of information to put up bias in a decision process, for example. So, is it possible? I don't know why the slides are behaving such. Anyway, can we use these attacks, so the adversarial perturbation attack, to defend against an unwanted soft biometric detection? Clearly, from a theoretical point of view, the answer is yes, but we have to think about it because adversarial perturbations are intended to be as invisible as possible because we want to mislead just the target CNN, but making the perturbed samples still being recognized as the real one by a human operator. What we want to do here is to trade this almost invisible perturbation in change of obtaining something that can be used in a real life scenario. So what we did is to design what is called an adversarial patch. So this picture here, so I'm talking about a little piece, very colorful piece that you can print and overlay over a person to hide his ethnicity. Clearly, the example reported here is about ethnicity and in particular about Black versus white people, but you can extend this attack to any kind of soft biometric. And as you can see from the results, the attack works, and it works also changing the position and the shape and the size of the shape. But we tried to as the title of the presentation says, adversarial perturbation in the wild. So it's not enough to do that in the digital domain. And we try to do also in the real world. So what we did was to do two different things. The first one was to print the perturbed image, so the image with the adversarial patch overimposed. And as you can see, it works also after printing, but we can also do a different thing. We can capture a picture in real time by using a webcam and add the patch in a digital way, and it still works. But you can also do another thing. You can do both things live. So you can archive a live video and use an adversarial patch in real time. Just want to pay attention that I'm overimposing over my face just to have a magnification of the effect because of time constraint. But as you can see, if I turn the patch and just show the background, I can cover almost all my face and I'm still being recognized as a white person. So in this first example, I showed you how it's possible to use adversarial perturbation to protect somehow your privacy, and in particular to defend against unwanted soft biometric collection. However, there are a lot of situations where people think that using biometric is fine and enforcing its security by means of deep learning is even better. A clear example for this is are the biometric authentication system, where people authorized, so are being recognized not for something they have with them, but for something they are. So for example, like the fingerprint. In this case, and in particular over the last year, CNN and deep learning is massively being used, and we can see we will see in the next few slides why. Among all, fingerprints are the most used biometrics because they are very, very easy to archive. And also they are felt like non-intrusive because it's very, very easy to just put your finger on a scanner instead of making a laser, for example, scan your iris. The problem is that with the rise of fingerprint-based authentication system, also, there was also an increase in the number of attacks designed against this system. And as the attacking such a system involved the presentation of a fake replica of the finger of the biometry, these attacks go under the name of presentation attacks because you are presenting a fake biometry. So, in order to protect against these attacks, it's possible to use liveness detection. And liveness detection is the task of recognizing whether the submitted replica, the submitted biometry, so for example, in this case, a finger, is coming from a real one, a living person, or from a fake replica. And as I was saying, since 2015, deep learning exploded also in this scenario, and the top performing approaches are nowadays all based on CNN. So the point is really fine using CNN in such critical context when we already know that they do have blind spots, so it's possible to mislead them. So the aim was in this case to show that it's not necessarily fine to use them by bypassing them. So by attacking a liveness detector based on a CNN. This is the attack scenario designed for the aim. So the idea was to inject a perturbation in the channel between the scanner and the liveness detection. And this is a real scenario because it's quite possible to attack that path. The point is that doing that is not straightforward because while, as I showed you, is very easy to attack a CNN by using an adversarial perturbation algorithm. In this case, we have to keep in mind that what we are attacking is not a natural image, but something with a lot of details that are known as minutia that are used to recognize the subject. So it's important to keep in mind that despite we want to inject a noise able to bypass the liveness detector, we also want this noise to not be so strong to the point of destroying the user details. And the point is that as I was telling, that fingerprint are very different from natural images. So if you apply a classical adversarial perturbation algorithm to a fingerprint image, you obtain something like that. This picture, I can tell you that it's totally able to mislead almost any type of liveness detection algorithm, but this is very different from a real fingerprint. So any kind of human operator will quickly say that this is not a real fingerprint. So what we did was to modify a set of adversarial perturbation attacks in order to keep in mind for two constraints. The first one is that only gray level perturbation are allowed, and the other one is that the perturbation is allowed only within a very reduced portion of the image. And I'm talking about the this region of interest, so only the portion of the image where the fingerprint is located. And the results showed that we tried several approaches. So the first one is known as fast gradient submitted. This is the first approach proposed in the literature. It's very easy to understand. Another one is deepful. This one is very, very powerful. And the third one, he reported as evolutive, is known as 1 pixel. And the last one is very interesting because it's not based on the gradient of the network. So while the first two are known as white box attack because they need to actually get access to the target CNN, the last one is gray box because it not really needs to get access to the network, but it just needs to be able to query the target system sometimes, a fixed number of times to get enough information to perform the attack. And as you can see from the reported numbers, this attack, the evolutive one, is very, very effective both against the liveness detection and against the authentication system. So it means that we're able to bypass the liveness detector without destroying the user details. More recently, and I'm talking about this year actually, we also did a step forward in that attack, and we moved from the digital domain to the physical domain. So we were able to further modify the attack in order to make it totally black box, as we now rely on a shadow classifier to craft the adversarial perturbation. So we are now totally black box. And moreover, we are able to physically craft the adversarially perturbed fingerprint and then physically submit it to a scanner. And this is very, very interesting because we proved that it's possible to move from the digital to the physical world. Finally, I want to spend just a couple of minutes about XI, Explainable AI, XI. Probably you have already heard about it, and a lot of people think that this is the panacea for all the problem deep learning has, because you can use explainable AI to understand the reason behind a decision made by a deep learning model. The point is that in our opinion, this is not fair and this is not true, because XI is a very interesting tool, but you don't have to think about it as as a silver bullet, because we know from the no free lunch theorem that there is nothing like free in the context of AI. So you already know that you can use XI to understand the reason behind the decision. So, for example, if we go back to the case of a cat versus dog, we can see that if we use GradCam, that is a very famous XI algorithm, to understand why the CNN made that decision, the algorithm tells us by using a heat map that most of the reason, the most important part of the image that led to that decision is the green one. So the face of the cat was the part of the image carrying all the information, or at least most of the information that made the network go for that decision. The idea here is to understand if, at what extent, is possible to mislead not only the CNN, but also the XI algorithm. So what I'm saying is that we want to make the target image being recognized as a dog instead of as a cat, but at the same time, we want to also mislead the XI algorithm. But what means misleading an XI algorithm? If you think about it, misleading it means making it still focus on the face of the cat while the algorithm is saying that it's a picture of a dog. And this is what we did. So we showed that actually it's quite simple to use adversarial perturbation to mislead the CNN while making the XI algorithm still thinking that is right in saying that the perturbed image is of a dog, and the reason why it's a dog is still because of the face. As you can see, well, the example made about cat versus dog, it's very, very easy to understand for a human, but we can perform this attack on a very different scenario. So for example, in the case of a biomedical image, and we can modify an MRI image, for example, saying that that person do have a tumor and we need to, they need to undergo surgery because of that portion of the image, while that image is totally clean. And clearly, you can see that this is very, very bad, because people may think that they are safe, they can feel safe because the XI algorithm is saying, yes, yeah, actually the reason because you need to that person need to undergo surgery is because of that portion of tissue, and that's not true. These are other examples. And as you can see, the attack is robust also against different type of XI algorithm. The one on the right is lying. So I tried to briefly describe a lot of situations, but all the points behind this presentation is that adversarial perturbations are not just a digital problem, they can be transposed to the real domain. Have you any questions, just feel free to ask. Also, if I was too fast, feel free to ask me to go deeper in a given point.
Thank you, Stefano, for the nice talk. So for anyone, if you have the questions, you can either unmute yourself, or you can also type your question in the chat so I can read it for you and let Stefano to answer your questions. Okay, let me just see. And meanwhile, in fact, at the same time, I have some questions, so I may just start. Yeah. So the first is so about your last several slides. You said that actually you can use this adversarial noise to somehow disturb your, for example, a CNN regression. Classification in that case to mislead the result of the prediction. So I was wondering, is that possible to do somehow in the other sense, which means here you try to attack, but is there some way to defend the system? For example, the most naive way is like, I will add much noise to the pictures and I will retrain my CNN so that it can be stable for this kind of noise. Do you have any thoughts on that, please?
Yeah, the point is that there are a lot of defense against this type of attacks, but since, none of them are a real solution because it's always a game between the attacker and the defender. So as soon as a defense algorithm is designed, a new attack arises and so on. So it's a game, or it's a war, as you prefer, between the attacker and the defender. So any kind of defense is not the final one. The one you proposed actually works, but not works really well because it works very, very good against a given adversarial perturbation algorithm, but it's quite simple to change some parameters of the attack to make it not longer being recognized as an adversarial attack.
Thank you. I see. So in that case, it's difficult like to cover all the randomness while you try to defend because it's the attacker who chose like the playground that they want to do that.
Exactly. And also you can defend only against public attacks, but I can imagine that there are a lot of attacks still under research that works, but that are still not public available. So against those you cannot defend. And despite you can think that this is a very research-oriented problem, it's a real one because people are starting attacking, for example, road signals against autonomous driving vehicles. And in that case, if you design an attack that works in a real-world scenario, and recently some researchers did that, but do not publicly release how to do that, you are able to mislead an autonomous vehicle, but people are not able to defend against this because it's not possible to retrain. And also, let's say that you got access to a data set with perturbation inside of it, you can retrain the model. It may not be straightforward to deploy the retrained version in your vehicle. So it's a problem, there are solutions, but it's not often straightforward to apply them.
Like in practice, it's always more difficult. Right? So I see there's a question from Claire in the chat. So nice talk, thanks, Stefano. Wouldn't eventually people be able to retrain their CNNs on images with added noise? Yeah, I think it's somehow the same part of the question as mine. And the second part is, or retrain images on the image with small regions with added noise.
Okay, the last part is very interesting because what you're proposing is not to attack the whole image, but just a portion of it. And if you think about it, it's what we did here. So it's what we did with fingerprint. We just attacked this portion of the image, not the whole image. You may retrain the network, but again, the problem is that it's a game, and you may be safe. You are safe up to the time a new attack arises. So it's not a final solution.
Thank you, Stefano, for your answer. And actually, I have another question for the explainable AI part. I'm not sure that I fully understand that. So for example, can we use the explainable AI? So as you said, if you look at the cat or dog, it's probably only the head of the cat that decides, the CNN decide to classify it. Does that mean when we use the noise, we only need to add, or we can somehow make a priority for noise for the adversary noise only on these parts? So if we have the CNN, we first do some explainable AI with some local model to locate the most important part of the neural network, and then we can add more noise specifically to that part. Yeah, I don't know if that's will be something feasible.
Actually, no, your point is very, very good, because this was our point. This was our idea. So we thought that probably if we perform an XI algorithm before, we can decide what part of the picture is important, and we attack everything but that part in order to preserve the XI output. Actually, what turned out is that almost all the XI algorithms are already vulnerable to adversarial perturbation. So it's not needed at all to perform this preprocessing stage. You can simply apply adversarial perturbation all over the image. And if you enforce a very low level perturbation, but distributed all over the image, the XI algorithm is no longer able to understand what's going on. So it keeps deciding for the wrong class by focusing on the same region of the image. And to some extent, this is expected, because in order to work, all the adversarial algorithms, explicitly or implicitly, tends to modify the important part of the image. But if they modify the important part of the image, the salient part of the image, actually also the new classification will be made based on those parts. So nothing's changed for the XI algorithm. And so the important part is that we cannot rely on XI algorithm anymore, because in the presence of adversarial, we are not able to recognize the presence of adversarial perturbation.
Okay, thank you. So maybe it's already like covered in your talk, that the idea of using the expandable AI to have like a more targeted attack. So let me see if there's other questions in the chat. Yeah, so meanwhile, so I think I am lucky today to have time to ask my questions. So I have another one is about application. So said actually you're now capable to make some physical print or physical like images which can disturb the real scanner. So I'm wondering if on application side, do you think that there's something that, so I think it's very cruel to do that with the physical applications, but is there any like application to like further in that direction?
Well, the point of my work, clearly I'm not the only one working on this task. Most of them are done in collaboration with other people. But in all the cases, the aim is not to perform a given attack just because of the pleasure of doing that, but usually to raise awareness about the risk associated with a misuse of AI in a given context. Okay. So in the case of fingerprint, we want to raise attention about the fact that critical application, security critical application, probably are not a good target for AI, or at least you need to be super aware of what's going on and what is the target, what do you want to obtain, and what are the risks associated with that. By realizing a physical finger, we can almost attack any kind of application based on fingerprint recognition. In the case of face recognition, that was more a work about a philosophical work to show that if agencies are going to use face recognition against people, there are ways to defend against that. So it was just, like a sort of provocatory work to not make agency use that. I know that our work was just a little one, just a little piece of work. It's not the final solution against the misuse of face recognition, for example, but at least we wanted to raise attention also about that aspect. The XI part, in my opinion, is one of the most interesting, because despite this is still in the digital domain, it is raising several concerns about its misuse, because as I was saying, more and more work, more and more people, research people, I mean, are saying, okay, my AI algorithm is good. You can use it in a real world scenario because I'm enforcing it, I'm making it trustworthy by using XI algorithm. But as we are showing that XI algorithms are vulnerable to adversarial attacks and there is no simple way to detect them, you can no longer say that it's safe to use your algorithm in critical domain, such like medical image analysis, because of the use of XI. So in my opinion, this is very important. And we are still working on that to make it more usable in a real life. So for example, we are now showing that you can use it in the medical domain and realize for example, a physical scan of the MRI. So I'm talking about the plastic image probably you have seen used by a doctor. And if you use that field with a CNN, it's being recognized as a tumor or no tumor, just as the opposite class. And it's very, very a severe concern, in my opinion.
Okay, I see. Thank you. Yeah, I think that definitely has like a more like a very wide range of applications for what you're doing here. Maybe not only limited to image as well.
Yeah, also the automotive. The point is that AI is 100% sure going to be our neighbor in the next few years, but actually it still is, okay? But let's say that it will be present everywhere in the last few years. So there is no way to avoid this. And this is good actually, because it's extremely powerful. The point is that we need to be aware of what we can do and what we cannot do. And so it's important to use it correctly in order to avoid misbehaviors.
Yeah, I totally agree with you on that point. It's important to, especially with now the fast develop of the AI algorithms.
Excellent.
Let's see from the audience if there is a final question for today. So if there's not, I think we can end today's session. So thank you again for Stefano for this very interesting talk. And thank you everyone for attending this data learning seminar. Yeah, so I wish you, Stefano, so you are in Italy, so you're one hour ahead of us in UK. Okay. So nice evening and nice for the end of the afternoon for everyone.
Thank you. Thank you again for this slot, and thank you for your attention. Have a nice day, all of you. Bye-bye.
Bye-bye.